Here's another example of determining molecular geometry, hybridization, and polarity. So let's take xenon tetrachloride for our molecule this time, and we will quickly do the Lewis dot structure. We end up with, we always just put things at 90 degrees in the dot structure. It has nothing to do with the shape really, it's just for our convenience in trying to look at it, and then after we get the dot structure done we can decide what the shape really would be. Okay, so I've got all those dots, but I haven't filled up enough dots, so I have to put in 2 more pairs, and xenon can definitely exceed the octet, so it has 2 extra lone pairs on the central atom, and there we are. So we look at the molecular geometry handout that I gave you, and we said how many electron groups do we have around the central atom? Well, we have 4 atoms, or 4 bonds, whether they're single or double or triple doesn't matter, plus 2 lone pairs. And we add that up and we get 6 electron groups. So we look in the column that's for 6 electron groups. One way of writing this, another way of saying what we have is we have the central atom, which is A. We have X, which is our peripheral atoms that are surrounding the central atom, and we have 4 of those. And lone pairs is E, and so we have 2 of those. So when you add the 4 and the 2, you get 6, and therefore you know that that is the column you're going to look in. You're going to look in the 6 column, which means that we're going to have an octahedral electron shape. So octahedral arrangement of our electron groups. And we can, right now, we can say octahedral. By the way, octa is 8, but that's for if the reason that it says 8 when we only have 6 things going out from it, which is a little confusing, is because if you close the figure, I'm going to have the figure like this, I'm going to make it like this, and these guys are coming out at us, and those guys are going back. Okay, octahedral. If you would close this figure up and just make flat planes connecting all of the corners, it would have 8 sides. The shape would have 8 sides. But just if you get that, fine. If you don't, just kind of memorize 6 electron groups is an octahedral shape. All right, so 6 electron groups, octahedral shape. We need to hybridize that before. Let's do that before we do the rest of the geometry, because as soon as we know 6, we know the hybridization. So the hybridization, we need to take 6 atomic orbitals and make it into 6 orbitals that can bond. If we have just the atom, we would have S and P's and then 5 D's, right? 1 S, this is an S, we have 3 P orbitals, and we have 5 D orbitals that are available for bonding. Empty or full, whatever, they're available. So we count off from the beginning. We need 6 of them, right? So we need 6. So 6 would be the S, and we always start with the lowest energy, of course. S, the 3 P's, and 2 of the D's. So if I would take those 6 orbitals, those are the things I'm going to pop in my magic bag and shake them until they all turn out the same. And so I'm going to call them S, P3, D2. I only need 6, so I'm not going to take all of the D's. I'm just going to take the ones that I need. So sp3d2 is our hybridization. As soon as you know your electron groups, you automatically know your hybridization. You just count off from the left side and get as many atomic orbitals as you need, collect them, pop them in your bag, and shake them until they are all the same as each other, and then you have 6 of them. And it turns out that they are going to orient themselves in this octahedral shape. So back over to the shape, we look at this and we say we've got 2 things up, right? 2 things up, 1 and down, 1 up and 1 down, and 4 things that are kind of in a plane perpendicular to that axis. Okay? Can you see that? The wedges are coming out at you, and the dashes are going back behind the paper. Electron groups are not created equal. Lone pairs are shorter and fatter than bonds. And so they come in closer to the central atom and they repel the others away from them. And so it turns out that what happens is the lone pairs are going to be on opposite sides of the axis from each other, trying to get away from each other. And we're going to get our 4 chlorines around the outside perimeter. So although the electron groups are octahedral, what we have here, when we name the shape of the molecule, we only look at the atoms. We've got our xenon in the middle, so what we end up with is xenon and chlorines coming out at us, and chlorines going back behind the board here, behind the paper, I should say. And so that is what we call a square. Let's see if I can write this today. Square planar shape for our molecule. Remember, we name the electron groups, considering every electron group, but we name the shape of the molecule only referring to the atoms. Now, is this a polar molecule? Last thing. Xenon and chlorine, I'm going to tip this on its, well, I think I should just keep it like this so that it's emphasizing the shape. Okay. Chlorine, 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 chlorine. Is this polar? Oh, yeah, I think they're polar bonds. So we can put our vectors in like that. Yeah. Xenon's not very electronegative. It really doesn't really care that much about electrons. It's pretty happy the way it was. It's okay with this bonding thing, but it really didn't need to. Chlorine really wants to complete its octet, so it's pretty electronegative, and we're going to have polarity like this. However, look how all those vectors are all pointing in opposite directions from each other. This vector here will cancel out this vector here exactly. Same length, same strength, same electronegativity difference, and opposite directions. And this one here will cancel out this one here. So even though we have polar bonds, the molecule is non-polar because all the polarity cancels out. And so the overall molecule is non-polar. So it's possible to have polar bonds and be non-polar as a molecule. What you have to be a non-polar molecule is you have to have 2 things true. Let's write that over here. To be polar molecule. I should say to be a polar molecule. Okay, we have to have 2 things. One, we have to have polar bonds. And number 2, we have to have some kind of an asymmetric geometry. Thinking back to the ammonia molecule, if you go up and down, you could say it was symmetric, but if you go side to side, you can cut through it with a plane and put the positive on one end of the side of the plane and the negative with the other. If I would cut through these molecules with a plane, these atoms in our xenon tetrachloride, the plane would go through every single atom because they're all in a planar arrangement. Everything is planar here, and so there's no way to cut through the molecule with a plane and get more negatives on one side and more positives on the other. So there's no positive end or negative end to this molecule. It is non-polar.